Hey, take a quick look around you, right now. I'll bet you can spot at least a dozen things made of plastic. You know, your mouse, the coffee maker, the case on your phone. They seem so simple, right? But behind every single one is this incredible story of precision engineering. So today, we're going to pull back the curtain on the process that makes it all possible, injection molding.
And listen, we're not just talking about simple little blocks here. We are surrounded by these unbelievably intricate plastic parts, with complex shapes and features that have to be absolutely perfect every single time.
I mean, think about complex gears inside some machine. They have to mesh together flawlessly, or the whole thing just won't work.
Or maybe something like these perfectly balanced fan blades, where even the tiniest little imperfection would cause a crazy wobble and a ton of noise.
All the way to the casings on the power tools we use every day, which have to be super lightweight but also tough enough to survive a drop from a ladder.
Which kind of begs the question, right? How on earth are millions of these complex parts made, with each one being a perfect carbon copy of the last? Well, the answer is this fascinating process called injection molding. And to really get our heads around how this all works, we're going to walk through a real-world case study, the design of a mold for two very specific parts, a rotor and a cover.
All right, here they are. Meet our main characters for this story. On the left, we've got the cover, and on the right, the rotor. Together, they're a key piece of an assembly for a two-wheeler. And yeah, they might look simple enough, but the engineering that goes into making them is anything but.
So, first things first. Before you can make anything, you have to choose the right ingredient, the right recipe. For these parts, the material of choice is a specific kind of plastic, nylon 6/6, which is reinforced with 13% glass fibers to make it extra tough. It's what's known as a thermoplastic, which really just means you can melt it down and reshape it. It's specially engineered to be super durable for tough automotive jobs.
And these properties right here are exactly why it's perfect for the job. Check this out. It has a really high melting temperature of 257 degrees Celsius. And its tensile strength is up to 118 megapascals, which is just a fancy way of saying you have to pull on it with a ton of force before it'll even think about breaking. This stuff is incredibly tough.
So where does all that toughness come from? Well, it's all in the chemistry. This is the material's molecular structure. You see these long, interconnected chains of atoms? That's the secret sauce. That's what gives this material its amazing strength and its ability to handle serious heat.
Okay, so we've got our super tough material. Now, how do we shape it? Well, that requires creating a really precise blueprint for the part, which in the world of injection molding means designing what's called the core and the cavity. The whole design process follows a pretty clear logical path. First, you analyze the part you want to make from every possible angle. Then, you create a detailed 3D digital model of the mold itself. After that, it's off to manufacturing to actually build it, and finally, you assemble it and do a bunch of trial runs to get everything just right.
Now, at the absolute heart of every single mold are these two halves, and it's a beautifully simple idea. The core, that's the bit that forms all the inside surfaces of the plastic part. You can think of it as the positive shape, the male half. Then you have the cavity, which forms all the outside surfaces. It's the negative space, the female half. When these two halves come together, that empty space between them is the exact shape of the part you want to make. Pretty clever, right?
So we have our material and we have the two perfect halves of our mold. The next challenge is, how do you get the molten plastic from the machine into that perfectly shaped void that's trapped between the core and the cavity?
This is where the feed system comes in. It's basically a delivery route. The hot liquid plastic gets injected through a main channel called the sprue. From there, it flows through these pathways called runners, and then finally enters the actual part shape through a tiny, super precise opening called the gate.
But hold on a second. We're injecting this molten plastic at extremely high pressure. We have to make sure it fills every last nook and cranny of the mold. So what stops those two big metal halves from just blowing apart?
The answer is a frankly immense amount of force. It's called clamping force, and it's all calculated based on the size of the parts and the insane pressure of the plastic. And get this, for just these two little parts, the math says you need a locking force of 2.5 tons. That is literally like parking a large SUV on top of the mold just to hold it shut while it's being filled. Wild.
So when you bring all these pieces together, the material science, the perfect mold design, the incredible pressures, you start to see the everyday objects around you in a completely new light.
You know, every single plastic object you own tells this exact story. It's a story of precision, where material science and thermodynamics and high-pressure physics and mechanical design all have to work together in perfect harmony just to create that simple-looking case or that little plastic gear.
So the next time you pick up a plastic object, any object, take a closer look. Think about the incredible journey that molten plastic took and the immense forces that were needed just to shape it. What hidden engineering story is it telling you?